So hi again, Bio30s. This brings us to our last lesson here. In this order I'm doing the pedigree charts last right now we're gonna because we're gonna talk about autosomal and sex linkage, and chapter 18 doesn't talk about sex linked at all. So pedigree chart is what you're looking at here. Okay, it records the transmission of one particular trait over several generations in a family. Let's look at how to read this. So this is from your data booklet. Males are square, females are circular. Affected individuals are shaded, and generations are the different levels. And we usually use Roman numerals, sometimes normal numbers like these numbers, in order to denotate them. All right. The rest of it you can like these people have mated and had children. If it's two lines, it's close relatives, and you know what that means. Identical twins are um, connected. Non-identical twins, notice that there's a connection up top here so that we know they're connected. These children are, of course, not twins. These two parents have two males and a female. All right. Um, Now, affected individuals, it means that they have the trait in question. It could be curly hair, all right? It could be straight hair. It doesn't matter. It could be brown eyes, blue eyes. They have the trait. The trait could be dominant. It could be recessive. It could be X dominant. It could be X linked recessive. Unaffected individuals don't have the trait. So as a reminder, we know that there's autosomal chromosomes and sex chromosomes. So we need to understand that there's autosomal inheritance and sex-linked inheritance. So let's take a look. If the trait is dominant, okay, therefore, and you should know this, homozygous and heterozygous individuals will express the traits. Okay, only offspring that have both recessive alleles will not show the trait. And if we're looking at this, for example, if this was an example of a Punnett square, we also know, not a Punnett square, excuse me, a pedigree, all right, pedigree, okay, not Punnett square. These aren't Punnett squares. I'm glad I made that mistake, because you're like, these aren't Punnett squares, okay? Each child is a reset, right? The Punnett square is the probability of one child inheriting the trait, okay? So you could run the Punnett square for these two individuals, that's fine. But the point is that if it's an autosomal dominant trait, the father has the trait here, all right? And here is the affected, right? So the father's affected, the mother is not. The mother is homozygous recessive, the father is heterozygous. Now we look at the offspring, okay? This male got the trait because he inherited that chromosome, which is carrying that gene from his dad. So did this girl. They inherited that chromosome. Now, mom can only give the recessive chromosome. So you notice that all four offspring have that chromosome. So these two are unaffected. Where'd they get this? Because dad is heterozygous and he's given each one his recessive chromosome. When we're looking at pedigrees and we're going to analyze them in class, I'm just going to get you set up, all right, for the types of pedigrees here and then analyze them in class. What we'll find is that for autosomal dominant, males, females are equally likely to have the trait because it's an autosomal trait. Okay, all autosomal traits have this. Traits do not skip generations because it's dominant, all right? It's a dominant trait. So, yeah. The trait is present whenever the corresponding gene is present, right? Heterozygous or homozygous. And there's male-to-male transmission. Why is this important? Because in some sex linkage, there's no male-to-male transmission. If it's a recessive trait, it's the opposite, right? You have the trait, you're affected if you are homozygous recessive. If you are homozygous dominant or heterozygous, you don't have the trait. So in this case, neither the mother or the father have the trait. They are unaffected by this trait, but they carry the trait. All right, what carry? Yeah, because they are Their phenotype is the dominant trait, but their genotype is heterozygous. So they have the recessive trait hidden within them. So if we look at the offspring here, all right, this young man has inherited both what I understand here, okay, to be the dominant chromosomes, and he's got one from dad and one from mom, okay? These two, all right, that we don't know where the chromosomes came from, but we can see that they got one dominant from mom, from dad, or vice versa, because they're both hetero and they both can, right? So let's say this boy, for example, got this chromosome from mom, he would have got this chromosome from dad. Let's say she got her dominant chromosome from mom and her recessive chromosome from dad. All right, but none of them are affected. Only one daughter has been affected. Why? Because she's got the recessive chromosome from mom and the recessive chromosome from dad here. All right, so what do we expect in the pedigrees? Again, it's autosomal, males and females equally likely. Traits often skip generations because it's recessive, and people, all right, that there's going to be less individuals with that genotype. There'll be more individuals with a genotype that produces the dominant trait. Often, both parents of offspring who have the trait are heterozygous, but they carry at least one copy of the allele. Parents, good, of offspring who have the trait. There we go. This offspring has the trait. The parents don't. What does that mean about them? They're going to be heterozygous. That's what that means. She has a trait, they don't. Why does she have the trait and they don't? Because they're both carrying it and they're going to give it to her. Only homozygous individuals have the traits. Only homozygous recessive individuals have the trait. Okay, traits may appear in siblings without in their parents. Siblings have this, she has a trait, the parents don't. It's the same as, okay, and let's just wait for it. Stupid thing. If a parent has the trait, those offspring who do not have it are heterozygous carriers, okay? So if the parent has the trait, we don't see that one here. We'll look at that example in class. We have X-linked as well. Sex-linked recessive traits. Okay, so X-linked as well. So, all right. For X-linked traits here, if it's dominant, you're going to, if you're a female, you're going to be heterozygous or homozygous. If you're a male, you just need one copy, all right? If it is X-linked recessive, if you're a female, you need to be homozygous recessive. If you're a male, you just need one copy. So for X linkage, the male actually, for males, it doesn't matter whether it's dominant or recessive. They're still going to express that trait because for males, remember, there's XY, right? And so you only need one copy of the allele in order to express the trait. So this has all kinds of interesting inheritance patterns to it. And the more we work with these things, the more we see what they are. So if it's X-linked dominant, all daughters of a male who have the trait will also have the trait. Why? Because if the male has the trait and he passes his X chromosomes to his daughters, okay, run the Punnett square and you can see that, all right? So the daughters will always have the trait if it's a dominant trait and the father has it. Why? Because the dad can only give that X chromosome. He doesn't have any other chromosome to give to his daughters. Okay? There's no male to male transmission. Why? Because the males, his boys, get his Y chromosome. All right? So there can be no male to male transmission if it's X linked. A female who has the trait may or may not pass the gene to son or daughter. Why? Because the female, if she has the trait, all right, and she's heterozygous, well, the males can, half the males will have the trait, half the males won't. If she has the trait, if she's heterozygous, because she's going to give a dominant X chromosome and a recessive X chromosome. 1, 2, right? So the male has a 50% chance of inheriting those X chromosomes, where they have 100% of inheriting their dad's Y chromosome. The females have a 100% chance of inheriting the one X chromosome from dad and a 50% chromosome of inheriting their mums. Why? Because the daughters will receive one of their mother's chromosomes. So if the female has a trait, right, and she's heterozygous, she may or may not pass the gene to their son or daughter. If she's homozygous and it's a dominant trait, then everybody gets the trait. She's going to pass it to everyone. Run the Punnett square, you'll see that. If it's X-linked recessive, the trait is far more common in males than females because the female has to be homozygous recessive. She has to have both copies, where the male will only have to have one copy of that trait. All daughters of a male who have the trait are heterozygous carriers. All daughters of a male who has a trait, if the male has the trait, okay, and the female doesn't have the trait, okay, if it's recessive, let's link back. If it's recessive, if mom has the trait, she is homozygous recessive, right? All daughters of a male who have the trait are heterozygous carriers. Is that the one I was working with? Oh goodness, I'm tired. I'm so sorry. Let's start that again. All daughters of a male who have the trait are heterozygous carriers. Okay, so the male has the trait, okay? It says X to the little r. He's going to give his X chromosome to each of his daughters, okay? And, oh, I'm sorry about that. And they'll at least carry it. If mom has the trait, all right, then the daughters can also have the trait. But at least they will have part of the trait, if that makes sense. This is what this is saying. All daughters of a male who have the trait it says are heterozygous carriers. I will say are at least heterozygous carriers. They will at least carry one copy of the recessive trait. The son of a female carrier has 50% chance of having the trait. The female, if she is heterozygous, the males will get either one of these X chromosomes, so they have a 50% chance of having the trait. There's no male-male to transmission because it's X chromosome, and males get their Y chromosome from their dad and their X chromosomes from their mother. Mothers of male who have the trait are either heterozygous carriers or homozygous and express the trait. Mothers of males who have the trait are either heterozygous carriers or homozygous and express the trait. Why? Because the male has to get his X chromosome from his mom. All right? She's either a carrier, she has one chromosome that has the recessive trait, or she's homozygous and she has both chromosomes that have the trait, and therefore all the sons will carry it in that point. Daughters of a female carriers, okay, again, the carriers are heterozygous, have a 50% chance of being carriers themselves because, right, if the female is a carrier, the daughters will get one of her chromosomes, right? One of those chromosomes is dominant, one is recessive. So, and we're talking about the recessive, right? So it's 50% in that case. So I know there's a lot here for you. One last thing is easy. If it's Y-linked, it's passed to all sons from their dads. 100% of the time, no exceptions. Okay. We're going to tease this out in class. We're going to work with the pedigrees that you see here, all right? Don't look at them or don't memorize what they are. It's better just to leave it alone and to let us work with them in class. Okay, I'm not even going to do this anymore. Oh goodness, my computer's slow. All right, thank you for your good attention. I hope that made sense. Questions, write them down and let me know how that goes for you, or excuse me, and ask your questions in class. Cheers.